Welcome back to Precalculus. We're jumping up to chapter 9, and we're going to talk about sequences and series. We're going to focus on just the first 3 sections of chapter 9. 9.1 is really an introduction to the topic, and then 9.2 and 9.3 are really where we're going to get into the meat of what we're going to be able to do. But 9.1 is just going to take its time introducing some notation and things like that. Some definitions, like for example here I wrote out the definition for sequence. It's an ordered list of numbers. Series, which we'll do the second half of today's class, will be a sum. Really, it's a sum of a sequence, so it's the numbers that are added together. So we'll talk about that. So usually with sequences, we're going to represent it with an a sub n. You're going to see that a lot. In many ways, this kind of is a whole different branch of algebra where it's notated differently. You know, a traditional algebra would use this f at x notation for a function, these parentheses, which is confusing. I always wish instead it was a subscript, would be nice. And so really sequences and series take up this subscript idea, and it's going to be really nice. You're going to see. Okay. So here is an example. Let me show you what it looks like of a sequence. A sub n equals 7 plus 5n. Notice n is primarily going to be our variable here. Instead of x, we're going to use n. N in mathematics is usually always an integer, and that's going to be true here too. It's going to be an unknown that can take on a varying number of values, but always an integer. So there's going to be some problems in the beginning. They're going to ask you to, let's just write it up here. Find the first 4 terms of this. Find the first 4 terms of the sequence described. And we'll call this, let's do 2 of these examples. So this one, the way you indicate the first term is you write A1. And the way you get A1 is by plugging in 1 for n. See, it's kind of like function notation where someone said, hey, what's f at x? And then they asked for f at 1. And then you plug in 1s for x, right? So A1 turns out to be 12. What's A2? Well, now you plug in 2 for n. And you get 17. What's A3? Now you plug in 3 for n. And you get 22. What's A4? Now you plug in 4 for n, and you get 27. Maybe you can see the pattern over here. Yeah, they're just increasing by 5, right? 5. I wonder why it's 5. Well, there's a 5 right there. In fact, you might even recognize this. And we'll make these connections more and more as we go. This is a linear equation, right? I mean, you could rewrite this like in the old days, like that. And we would call that the slope. Slope is also called rate of change, right? So that is how quickly it is changing over here. This is called the y-intercept in the old days, or initial value. And actually, if you wanted to find A0, it would have been 7. And the question becomes a lot of time, what do you mean by initial? Is this the initial? Would you call this the first term in this sequence? If so, that's kind of an odd precedent to set, because then this would be the second term, this would be the third, this would be the fourth. Why is that odd? Because the first A1 is the second term, A2 is the third. This is where we get into this confusion that we don't really have a consensus on. Do you start at 0 or do you start at 1? Well, calendars start at 1, right? April 1st, December 1st, whatever you're talking about. Stopwatches, though, start at 0. So I think 0 makes the most sense, but it is kind of confusing. Because you might say the first term in this sequence is 7. But the first term is when you plug in 0. The second term is when you plug in 1. So that's going to be a bit confusing. And a problem like this, when they say first 4, they're going to want you to start with A1. but we'll discuss that more as we go. The second one, we'll make 4n times -1 to the n, a little more intriguing. So if we want to find the first 4 terms, and we'll start with, so this is not a linear equation, so it's going to be a bit different. Plug in 1 first, and that's going to give us 4 times -1, -4. Plug in 2, that'd be 8 times, well, 1, 8 times 1. Do you see what's going to happen here? 12 times, no matter what that power is, it's just bouncing from -1 to 1, -1 to 1. So this is going to be -12. And it's going to be 16 times 1, so 16. So you can see they are changing signs. This little thing right here, sometimes I call it, it's a sign changer. It's like a little mechanism that changes the signs from one term to the next. What would happen if that instead was n plus 1? Think about that. Well, when you put in 0, or when you put in 1, you get a 2. So it would start as evens, right? It'd be even, odd, even, odd, even, odd, instead of odd, even, odd, even. What if it was a n plus 2? What would be different? Nothing. Yeah, it'd be exactly the same as n. Isn't that interesting? Because it's just, all we're looking at is it even or odd? So n plus 2 and n is going to be the same in terms of even and odd. So n plus 2 would be the same as n plus 6, be the same as n plus 100, n plus 1,000. N plus 1 would be the same as n plus 99, but the same as n plus 555. So kind of a fun little fact there. Again, this section is just a lot of kind of random things. 9.2 and 9.3 really bring it together. So hang in there as we introduce this. Next up, we're going to just get a chance to try to write our own, an equation for a sub n, that looks like an, describing the sequence that I'm about to show you. Okay, so 2, 1, 4/5, ooh, 5/7, ooh, 6/9, 7/11. Now, odd thing about 6/9 is, why would you write 6/9? Who writes 6/9? It's 2/3, right? Who doesn't reduce that? Well, there was maybe a purpose for that. Let's see. Do you see a pattern? Well, 2 and 1 seems like there's a clear pattern, but then it's all thrown off when you go to fractions. But let's focus on the fraction portion and notice what's happening here. They're increasing by 1, right? What's happening here? They're increasing by 2. So what number should have been here? They shouldn't have put a 1 here. What were they thinking? I'm going to just kiddingly mark it off. It should have been 3/3. Hey, that is 1. And this shouldn't have been 2, right? It should be 1 less than the numerator, and 2 less than the denominator. It should have been, 2/1. Okay, now we see what's happening. So the sequence that describes this is the numerator, notice, goes 2, 3, 4, 5, 6, 7. How do we model that? Well, it's increasing by 1, right? Remember what we learned over here? This was increasing by 5 up here. So I had a 5n. This one's increasing by 1, so I just need to have an n. But the 7 was kind of your starting point when n was 0. So if you were to go, if you were to go back one more, this might be interesting to think about. If you were to go back one more, I hadn't really thought about this. This would be, it would be 1 over -1. So this needs to be, I should have written this a little differently. Whoops. Let me make this into a fraction over here. because we're going to be dealing with the numerator and denominator separately. So this needs to be n plus 1. So do you see how when you plug in 1 for n, you get this one. When you plug in 2 for n, you get this one. When you plug in 3 for n, you get this one. When you plug in 4, you get that. 5, you get that. So n plus 1, it kind of jump starts it, saying don't start at 1, start at 2, but then go up by 1. In the denominator, we go, let's do a different color, 1, 3, 5, 7, 9, 11. What is it increasing by? It's increasing by 2, so it must be 2n. But you want to start at 1. I mean, if n were 1, you'd be at 2, right? So if n were, if n was 0, you'd go 2, 4, 6, 8. So it's just 1, it's 1 too big always. So what do I do? I just do minus 1. And that way it accounts for it. And you could see that this, I don't think I really need to write this, but that is the 0 term, and it would work. If n were 0, I get 1 over negative 1. So this is really found by feel. There's not necessarily a formula yet. 9.2 and 9.3 will introduce formulas, so some of you will probably hate these problems that you are figuring out by feel, but I think they're kind of fun, just a little bit of trial and error. And again, hang in there, we'll add a little more form to it later. We need to introduce a few more things, 2 more items before we wrap this video up. Next up is what's called the factorial. So I'm sure you guys have seen this. I know even in geometry, if you had me, we did this with a little probability introduction. So the factorial is indicated with an exclamation mark. So if someone says x factorial, they mean x times 1 less than x times 2 less than x times 3 less than x, and you go on and on and on until you get to 1. So I guess if x was 1, it would just be 1. X is 2, it's 2 times 1. Maybe I should even show this. 3, 2, 1. So you work your way all the way down to 1. Let me show what I mean with an example. So when someone says 5 factorial, you could put this in your calculator. Hit 5. If you have a TI 83 or 84, you're going to hit math. I think it's the 4th option down, factorial. After you hit math, maybe you have to go over the probability. I think that's right. Yeah, probability, 4th one down. This means 5 times 4 times 3 times 2 times 1, which is, let's see, 2, 6, 24, 120. 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And this, I'm not going to work it out, but it's 40,320. You'll note that factorials get really big very fast. In fact, you can't even do 100 factorial in your calculator. I think 70 or so is as high as it goes. What if you were asked to do 8 factorial over 5 factorial? Well, I'm guessing you're probably thinking, oh, just plug those in and you get 40,320 over 120. I don't know what that is, though. A better way to do it, I'm going to even mark that through. Let's just write out what we have. We have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. Notice the 1's cancel, the 2's cancel, the 3's cancel, the 4's cancel, the 5's cancel. I just have 8 times 7 times 6, and that is 336. Another way you could write this, some people will do it, is they'll say that's 5 factorial. This is 8 times 7 times 6 times 5 factorial, and get the same thing. But rather than calculating both factorials, this is the way to go. Sometimes you may encounter a situation where you're like 100 over 99 factorial. Your calculator can't even evaluate either one, but we know the 99s we cancel out, the 98s we cancel the 96, all the way down. It's just equal to 100, right? 100 factorial over 99 factorial would be 100. Now there's some in your homework, I'm sure, that look like this as well. They probably have a disclaimer here that n is bigger than 0 or something like that. Yeah, 1 or greater, something like that. So what would this be? Well, let's just write it out. We know that when you do a factorial, you write the same number that's before the exclamation mark first, then you do that number minus 1. So what's 2n plus 1, a minus 1? Like, oh, that's just 2n. And then it would be 2n minus 1. And then 2n minus 1 minus 1, which is 2n minus 2. Do you see what's going to happen? Then it's 2n minus 3, and you just keep going on and on. Down below, we have 2n minus 1. Hey, that's familiar. That's the same as this one. The next one would be 2n minus 2. Well, there it is. Yeah, all the rest are going to cancel. And the only survivors are these two. So you're left with 2n plus 1 times 2n. I don't know, I guess you could multiply it out if you wanted. 4n squared plus 2n. I'd probably leave it not multiplied. So that's a bit on factorials. One last topic before we wrap up this video. Looks like we're at the 16-minute mark here. And we have one more 9-1 video to come, is an idea called recursive sequences. And students tend to really like this at first and kind of want to do this all the time. But this has major limitations. Let me show you how you can do that. A recursive sequence is going to give you a couple of term information about a couple of terms. Like say the 0 term is 12, the first term is 17, and each subsequent term is that. And I probably didn't even need to mention. I don't know why I mentioned this. Let's just get rid of this. So let's say, see if I can move that up. Hey, look at that. Let's say that you're told that a sequence starts with 12, and then this says if you want a particular term, take the previous term and add 5. So I really want the first term. Well, I better take the previous term and add 5 to it. So A1 is going to be 17. A2, I really want A2. Well, you better take the previous term, A1, and add 5 to it. So it would be 17 plus 5. And there is definitely a better way to do this one. This one does not have to be defined recursively. So do you see how the an minus 1 is, the subscript is 1 less than an. So that means previous. So this would be 22 plus 5, 27. So we see our sequence here is 12, 17, 22, 27. They go 32, we go 37. We can do that, right? But what if someone said, hey, can you give me the 85th term? This would be a horrible exercise, right? You'd have to find the 84th to get the 85th. Well, how do you get the 84th? You got to find the 83rd. How do you get the 83rd? On and on and on until you get back to, I guess, A3, the one that we know. So there is a way to define this explicitly, which I did earlier, and we'll be focusing on that in 9.2 and 9.3. This one you could. Well, I'll just tell you what it would be. Why not? Explicitly, it would be the nth term. It'd be 5n plus 7 plus 12. Yeah, 5n plus 12, because the 0 term is 12. But again, that's not always possible. So the idea of recursive sequences is there are sequences where you can't define them explicitly. Let's take a look at the most famous. I'm going to leave a space for the name. It is 1. 1, what a weird start to a sequence, right? The same number twice. 2, recognize this? Not 2 next, but 3, 5, 8. Okay, I'm not even looking at my notes. I have this memorized. I'm that sort of a nerd to memorize this. Who would memorize something like this? So it goes on and on and on. How am I doing this in my head? Well, 144 next, right? How am I doing this in my head? Well, because it's got a pattern. And this, by the way, is called what? This is called the famous Fibonacci sequence. In Fibonacci sequence, you see this all over the place in nature. If you look at a flower, it's going to have the number of petals will be one of these, most likely. That's why you don't see 4-leaf clovers. There's no 4 on here, right? So flower petals. Pine cones. If you count the little petals on a pine cone, you're probably going to see, I don't know, one of these numbers. If you count the little spikes on a pineapple, you're going to see one of these numbers. It's crazy. So we see in creation lots of these numbers from the Fibonacci sequence. So let's see how we can actually define this. Where are these numbers coming from? Did I really memorize them? No, I don't memorize them. There's a pattern. So do you see it? So Fibonacci sequence, you have to actually define the first two values in the sequence, and then you can define the next ones like this. You could say, you want a particular term, you need to take the previous term and add to it what? The term before that. So that right there is a definition of the Fibonacci sequence. Some people might prefer to write this as an plus 1 equals an plus an minus 1. That's the same thing. So this, I would say, you want the current term, take the previous plus the one before that. This one says you want the next term, take the current term plus the one before that. Same idea. So what I was doing is I take these two, I add to get 2. I take these two, I add to get 3. I take these two, I add to get 5. I take these two, I add to get 8. I add to get 13. I add to get 21. I add to get 34. I add to get 55. So it goes on and on and on. And again, this is the thing we see in nature so much. Really kind of cool. The Fibonacci sequence. So we're not going to say a whole lot more about that, but let me just show you one more recursive sequence and this video will be complete. What if they said, write, again, the first 4 terms of the sequence, and it's defined this way. The first term is 32, and the n plus 1 term is a sub n over 2. What is this even talking about? Well, the first term would be 32. The next one. So this is written this way. Let me just say this again. This is the same. So this is saying you want the next term, take the current term and divide by 2. 16. Or you want the nth term, take the previous term and divide by 2. Same thing. So this is just a halving, and I'm just going to keep going here. Why not? So that's what that sequence would look like. And I went beyond 4, and I did like 8. Okay, so that's a good start. We're going to jump into the series part of this section next.